Good day. My name is Daniel Pistelli, and today I'm going to talk about the security of non-executable files. Now, I knew that this was the last speech, so I tried to make it not too boring, but I guess by now you are so pumped up with adrenaline from dodging chocolate bullets that you should be able to follow. So, in the recent years, we have seen a rise of non-executable files which infected systems or compromised security. Non-executable file, we should start defining what is a non-executable file. That's not so easy, actually. The term I used is actually quite a broad one. The problem is giving a very precise definition. A non-executable file, let's say a PDF with JavaScript, would you call it an executable file? Probably not, but this JavaScript is going to be executed at some point, probably. So you would certainly call an executable file Windows executable, probably even a .NET assembly. Why? Well, a .NET assembly is wrapped up in the same format of native executable files. So it's apparent to even an unskilled user that a .NET assembly is an executable file. But let's take, for instance, a Shockwave Flash application. Shockwave Flash application contains bytecode, managed code, just like .NET assembly. They're not the same, of course. I don't want to say that. But they have some similarities. The problem is often perception. The barriers between non-executable files and executable files are very thin. And often the problem is perception. Now, let's say the most feared issue when we're talking about non-executable files is infection, of course. The most common vectors for infection are scripting or bytecode, shellcode, meaning buffer overflows, and dangerous format features. Now we'll analyze them one by one. Scripting and bytecode. Scripting is, let's say, very functional, but whenever there's functionality, security suffers from it. There are two types of files, basically. Those which offer scripting just as a capability, as an additional capability. Oops. Well, how do you like that? And those files which completely rely on it. For instance, Flash applications. I heard many times users refer to videos on Google or YouTube as Flash videos. Of course, this is very misleading because what happens actually is the browser is downloading a Flash application which contains code, and this code actually plays the video. It's very different from downloading a video. Here we see, well, this is just the code of Google video, which I don't know why. It's stuck. The computer has crashed. Great. I have to reboot, I'm sorry. No, it didn't. Then it's, I don't know. No, just PowerPoint crashed. Perfect. Okay. Really sorry about this. Oh. Goes with, yeah. And now, thank you. Okay, oh, sorry. Now, when we're talking about scripting and bytecode, what happens is that they usually exploit the technology itself or the API it provides. But what about Visual Basic application? You remember those contained even in old Office documents. Here we can see, I don't know, it's very small, the font. I don't know if you can read it, but here we have basically some Visual Basic application code which creates. It's not my day. I'm sorry. It's not my day. Okay. Well, can we do it without slides? No, I don't think so. Yes. Perfect. All right. Well, okay, I don't want to stall now the situation, but okay, let's see. Come on. Yes. Okay. Sorry about the waiting. Okay. All right. Let's go back to the part. All right. It basically creates a regedit file on the disk and then executes it. When we have such type of scripting or bytecode functionality which access the system API, it's no longer a document. Actually, in that case, it's really an executable. Because the power it has is limitless. So it does make sense, of course, running a certain bytecode or managed code into a sandbox like Flash, of course. Many file formats contain code, even without experts knowing it. I just recently became aware of the fact that even QuickTime movies can embed JavaScript. Shellcode, okay. This is what you don't want to happen, of course, when you open a file. Buffer overflows are usually triggered by script or bytecode and its APIs, or by file format parsing issues. Tampering, of course, with string and their sizes is a very good way to obtain a buffer overflow. How to detect zero-day shellcode exploits? Well, one way is to emulate the scripting and bytecode environment, but this is not a good approach because usually buffer overflows are implementation specific. So in this case, it's mostly useless. It's difficult because it takes a lot of work. It's slow, and it's also risky because a buffer overflow can happen even in our emulator, of course. Detecting issues in the format is a very good indicator for buffer overflows, but it's impractical to validate everything. It's not always possible because some documents have parts which are undocumented or are vendor-specific, and it may not be triggered, I mean the shellcode, the buffer overflow, by malformed data. It actually could be triggered by data which is completely genuine according to the specification. Here we have a very simple shellcode signature. Well, in this case, it's not really a shellcode. In this case, this malware PDF embeds a Windows executable. So we're detecting lots of shellcodes, but it's just to give an idea. If the shellcodes uses a very easy to detect signature, we can base on it to detect it. But here we see, I want to show you a more difficult case. Here we have a JavaScript shellcode vector. Now, let's see. Okay, this is strange. It should show a video, and it happened even before. It's probably because of the, yes, it is stuck, probably because I have attached the cable for the, it didn't do this before, so it was working, I checked this. It's stuck because of that. It crashes because of that. Great PowerPoint. Okay. Changes. Let's see if I can do it with another resolution. Yeah, now it works. Keep it this way because otherwise it crashes. I'm sorry. You can still see it, probably. Yes. Okay. Now here we can see a very common JavaScript infection vector. It basically does some operation on a string and then uses it to execute shellcode, exploiting, of course, a bug, a vulnerability. And if we dump this the string on which operations have been performed, we can disassemble the code. Now, here we see the shellcode disassembled, and it uses a very common, it's very common. I mean, it just jumps to the call. The call pushes on the stack the instruction pointer, which is actually the data after the call. The code above just pops the instruction pointer from the stack and starts decrypting the code, data actually in this case, below the call. It goes on decrypting until it finds a signature, which is this DA, and we can just decrypt it very easily because it's a very basic encryption. And now we can see the code, of course, after having it decrypted. Now, this shellcode is very easy, it's very common. It just gets the PIB from the process, then goes through all modules, tries to find kernel 32 DLL, uses a very simple hashing technique to retrieve the original API names. It needs some APIs, so it uses this technique and then uses these APIs. It tries to find the open handle to the currently open PDF, dumps the executable it has in it, and executes it. Nothing special actually here, but what is to mention is that in this case, the detection of shellcode through signatures becomes difficult when the shellcode uses a loader, either to avoid 0 bytes or detection, or the loader can be polymorphic or even obfuscated. In this case, it's still easy to identify the issue because JavaScript is used. The worst case for detection is a buffer overflow triggered by a format parsing issue. Even worse, when the data triggering the issue is valid according to the format specification. Dangerous format features, and here credit goes to Didier Stevens, who at the beginning of 2010 posted on his blog a very effective exploit which basically just launched an executable from Foxit Reader when opening a PDF without asking the user. The technique is actually very, very easy. It just uses the launch. This is a PDF object. Here we have a launch action object, and it launches cmd.x. denial of service attacks. Sometimes the goal of the malformed or the, let's say, malicious file is not to infect a system, but just to cause unresponsiveness or make the handler of the file crash. Denial of service attacks are best carried out through format parsing issues, and code execution might require, because this is the point. Code execution, like JavaScript, might require user interaction, or the user could have JavaScript completely disabled. But when we have a format parsing issue, the parsing is never conditional. If it is, the outcome of that condition can be determined by the format itself, usually. So it's the lowest layer. If we can somehow get the parser, I mean, if we can get to read it and not validate our data, we can probably get it to crash or become unresponsive. Common problems when parsing files are pointer arithmetic, integer overflows, division by zero, loops, unpacking, and recursive references. Pointer arithmetic is very easy. We get a value from the file, we perform a arithmetic on it, we get a new pointer from it, and in the best case, the result is an access violation. Integer overflows. Many languages have types which are limited to their bit size. So if we read a value from the file, add it to another value, we could get a value which is lower than expected. Then we have loops. This is very, very common. A loop, in this case, we take a value from the file, a numeric value. We put it in a loop, and without verifying if the value is too big, if task, the function which is called by the loop in this case, performs, allocates memory and stuff like that, it will exhaust memory. Or the application becomes unresponsive. Unpacking, this is very, very common as well. It happens when, for instance, we have decompression. Decompressed data can be much, much smaller than the decompressed one. So if the handler of the file doesn't put a limit on the unpacked data, well, it could easily exhaust either virtual memory or disk space. Then the best the best solution is to force the document to declare upfront how big the decompressed size will be. This is used by many file formats. XML bombs is another example. In this case, nothing gets decompressed, but data gets expanded, and it's the same problem. Okay. Recursive references. This is probably the trickiest case because it is difficult to catch at times. You may have in your application, which is parsing a particular file format, a recursive reference case in which you are parsing elements, and elements are specifying directly the next or previous element in the sequence. So common cases are linked list or trees. The result is either an infinite loop or even recursion. In this case, it will very probably exhaust memory. Okay, here we have a recursive list. As you can see, the fourth element goes back to the first. So if your application doesn't check this recursion, it will go on forever. A recursive tree. Trees are usually parsed by using recursive calls inside the code. So, in fact, many years ago, I wrote an application called CFF Explorer, and just recently, Ange Albertini reported to me a bug in which basically this application parses Windows executables, and one of the things it does, it parses resources. Resources inside Windows executables are structured in a tree. So it doesn't check for recursion, and it exhausts the stack, so it gets terminated. How does malware avoid detection? Well, there are various ways. Of course, I won't list them all. Some ways are code obfuscation and reflection, file embedding, encryption, and external references. Code obfuscation and reflection. Here we have a typical JavaScript obfuscated sample. Let's beautify it a bit, otherwise it's impossible to read. If you can, I don't know if you see it, at the end we have as an assignment. This basically assigns to the variable e the evil string, which then is used to call code which is put together above. This is a typical case in which the code is obfuscated and it uses reflection. Evil is the way JavaScript uses reflection. File embedding is very, very common. I did a very, very neat test on this. And I took basically a random PDF malware. I have uploaded it to VirusTotal, and 31 out of 44 scan engines detected it as a malware. It is an old malware, an old PDF malware. What I did afterwards is I used Didier Stevens' embed Python script to embed a PDF into another PDF or another file. I mean, in this case, I embedded a PDF into another PDF. And what happened in this case is that now only 24 out of 43 scan engines detected the issue. So already some scan engines can't follow it anymore, probably because they are not parsing the PDF format. They are probably just checking for a signature, or I don't know, probably relying on hash, I don't know. Now, the same script by Didier allows to, by specifying this S option, to rename the embedded files string in the PDF catalog. It actually just changed the F from upper to lowercase, nothing else. And now only, how many? Yeah, 20 out of 43 scan engines. So every time I do something, less and less engines find the issue. I went one step further because the object, the embedded PDF, was still using the original, well, it was already still there. It was removed from the catalog, basically, but it had still the embedded file type. So what I did is just rename the type to embedded xile. I just put X instead of an F. And, well, now only 13, actually, out of 43 scan engines. So we went from, I don't know, more than 30 to 13. Of course, it should be clear, it is no longer accessible in the same way as before. Before, the embedded object was part of the PDF format, and it followed the rules of the PDF specification. I renamed it, and probably it's not accessible as easy as it was before, but it's still there, and nobody catches it. I mean, still someone catches it, but 20 fell out from catching it. Yeah, malware might, however, not be stored at a format defined location. In this case, it is easy, of course, to check for embedded file into a PDF object because it relies on a special, I want to say, type to mark that it is using an embedded file. Not always the case, of course. The embedded file could be encrypted or compressed. In that case, it becomes even more difficult. Here we have cryptool, which is performing some analysis on frequency patterns. This is, of course, a possibility when we have encrypted malware. We cannot really identify probably a file if we don't know how it is encrypted. And a way is to perform statistical analysis. More on that later. Here we have still encryption. It is still possible to detect an embedded file which is using encryption, if it is using only XOR encryption. it becomes difficult to precisely locate and decrypt if it is more complex, the encryption, of course. The same analysis that we seen before for embedded files, meaning statistical analysis, can be used for encrypted files, but it can only tell us that something is wrong with the file and help us locate it, but it is not precise, and it doesn't tell us how to decrypt it, of course. We'll see more on that later when talking about locating foreign data. External resources. This is a technique in which main file loads either an external file and uses it, or the main file accesses resources contained in external files. If we go to the Adobe site, here's a very small code snippet in which URL request loads an external Flash file and displays it. Now, this is possible to do even with a remote Flash file, which brings us to the next issue, the violation of trust. It is possible, in some cases, we did some tests, to load a Flash file in a page which is blacklisted. It doesn't work always, but in some specific cases, we tested with Internet Explorer in some cases, and with Firefox. In some cases, this does work. This means that the Flash file is probably, the main Flash file is probably in a whitelist page. The other Flash file is blacklisted or not in a whitelist, but it still gets loaded from the main file. This security issue is a transition from trusted to untrusted without the user noticing. Now, it is clear that since we have embedded files and external resources, we should see a file as a container, as a file system, actually. This is the abstraction which should be used when looking at a file. I've built myself a very silly Flash file, which has a very complex hierarchy of embedded files. We can see it contains one file after another. It's just silly, but it illustrates what can be achieved by embedding and or using external resources. This is why it should be seen as a file system, in a sense. Now, some security considerations. I'll try to make it not too slow here because it's not that exciting. Now, software updates, of course, are essential, but they don't protect against 0 days. Many users don't update their applications, like myself, as we have seen before. Scripting and bytecode. Now, it's better to disable in a secure environment, of course, and could be filtered out before it reaches workstations, but it's not always possible, as we'll see later. Oh, now this is interesting, internet files. It is possible to hijack, of course, a request over HTTP. A malicious Flash file could be served instead of the originally requested one. A solution is, of course, to use HTTPS with a whitelist of certificates and maybe enforce it for certain file types, or enforce it always, I don't know. Now, digital signatures. They guarantee the origin of a file. There are two types of digital signatures: external, like when we use a program like OpenSSL or PGP, or embedded. Signing. Does signing make sense? Yes, it makes sense when the communication is insecure, the medium is insecure, like the internet. SSL can only guarantee that a file comes directly from a server, but it tells us nothing about the security of the file of the server itself, which may have already been compromised. It is reasonable to believe that the security of the workstations used to sign a file are higher than that of a server. I mean, this is, I hope at least. External signatures. They have advantages. They apply to every file and are handled the same for every file type. This is, of course, self-evident. If we have OpenSSL or PGP and we sign a file, the signature will always be in the same format for every file and handled the same. The cons, it is a bit impractical because, for instance, and it might be confusing for inexperienced users. Impractical because it forces for every file to have an attached signature. Embedded signatures. In this case, the signature is embedded in the file format itself and not an external file. It is practical. This is the only advantage which I could come up with. It is not always, the concept, it is not always supported. There are many file formats which don't support this at all. It's implementation specific, and because it uses standard cryptographic algorithms to create the signature, but the way it is stored inside the file is totally custom because it needs to consider the file format itself. If, for instance, we are hashing the file, we should, of course, ignore certain parts which contain the signature. It might require also the document to be loaded by the handler for verification. If we have a PDF which is signed and you need to open the PDF before validating the signature, it becomes kind of useless, as you cannot understand. And it's also cumbersome to manage all this signing from a centralized point, because every file type has its own format, its own rules, and there is no way to centrally manage this. Data carriage, yes, this is interesting. Data carriage is when a document is used to transport data, and this kind of data can be either internal, like indiscriminate, like metadata, or targeted, or even external, like malware. When we have internal data, it can be personal information. Files can, in fact, contain a surprising amount of personal information, like the author which created the document or edited it. And this kind of information can be trivial geolocation data, like in JPEG files. Here we have a JPEG file with geolocation. Actually, it's good that it's not that common, actually, and this is good. But it can be even much more uncanny. In this case, for instance, I don't know if you can see it, but we have signed CFB document, in this case, Office document, and it contains the Windows version it was created on, the Office version, the application version, which is the same, the monitors, the number of monitors we're using, the horizontal and vertical resolution of our screen, the color depth. I mean, I don't know what's the purpose of this data. I'm surprised too when I saw this. If you don't believe it, yeah, it's too small, but you cannot see it, but here is the unformatted XML which contains this data. I don't know what they were thinking when they put this data inside. Now, after having established that there is such kind of data transportation, we need to locate this foreign data. It is very common to append data at the end of a file, custom data meaning, not part of the file format, but there are more sophisticated cases like data hidden among parts of the file format or data stored inside custom data containers of the file format itself. Here we have JPEG custom data. Now, if this bar, I don't know if you can see it, contains the kind of data contained in the file. The white is essential data for the JPEG itself. The gray here is custom data, meaning data which is not essential to the file. In this case, it's vendor-specific data. You cannot see it, but there's a Photoshop string inside this data, and it clearly was added by Photoshop. Now, the yellow is the visible data in the hex view. Now, here is the same data seen from the format perspective. It is here, it uses an up marker. The up marker is, yes, the up marker is the way of embedding custom vendor-specific data inside a JPEG. Okay, here we have I was quite surprised when I opened a holiday JPEG I did during my holidays, because I don't know if you can see it, but at the end of this bar, there's a very red thin line which marks foreign data. Red is foreign data, which means that it's not part of the file format. So what I did is look at the data. I recognized it being an embedded JPEG because it started with the D8. D8, this is the initial marker for every JPEG. It was missing a prefix, the FF prefix, so I dumped the data to file, I added the prefix, I opened it, and this is the image appended to the file. So it's just a thumbnail of the original image. But what is strange is that usually thumbnails are embedded into JPEG files using the EXIF format. The EXIF format is specified using the up1 marker inside JPEGs. It's possible also to insert geolocation inside the thumbnail itself, so it's kind of very useful to know what a file contains and its embedded files. Here we have a PDF carrying malware. Here we have the red data, which is the foreign data. To a trained eye, it's very easy to recognize that, that it embeds XORed Windows executable. It is easy also to extract the decryption key for this XORed executable, because the initial part of a PA, of a Windows executable, is full of zeros, so it was easy to extract the key. We decrypt it, and here we have the Windows executable. Steganography. I'm not an expert in steganography, but I need to mention it because there are some topics which are related to the one at hand. And with foreign data, it's possible to see what's hidden inside of a file because, well, it's different in with steganography because the payload which is hidden using the data of the file itself. The secret data is, it is on purpose to avoid detection, of course. Data could be hidden inside recurring data elements of the hosting file, or another method is to change the frequency or the order of something to encode data. There are many other ways, but I cannot list them all. Some points about steganography is it is important to note that hidden data must be much less than the data of the host file, because otherwise it would be evident that the data is hiding something. Steganography is expensive in terms of disk space, and this is why common carriers for steganographic data are media files. They are already large. Here we have a bitmap containing a Windows executable, and it uses a very basic steganographic technique. It basically just changes the least significant bit of every byte in an RGB color component. This means that every color is just slightly modified compared to the original one. If you can see the original and the carrier, they are the same. I actually confronted them even on a big screen. It's impossible to notice just by looking at them. The way to detect this is to use some analyzing techniques. The least significant bit technique is can be discovered by by analyzing the noise in the picture. Again, detection are usually statistical, the methods involved. The file might look suspicious if the output of various algorithms is considerably different from the output of many normal files of the same type. This means we have a large amount of files which are very common. We use some algorithms on them, and we confront the output with the output of a particular file, just to see if they are if there is an anomaly, let's say, okay. Just in the case of embedded files, statistical analysis can only point in the direction of something, and it's not conclusive, of course. And one last thing, it is very important to process the format before performing analysis. Doing just bulk analysis on a file is kind of, it results in false positives or may even not detect something. embedded devices. Now, the use of embedded devices has increased in recent years, always more, and only recently the jailbreak for the iPhone and iPad was available as a PDF. The jailbreak exploited two vulnerabilities. The first one allowed to escape the sandbox, the user mode sandbox for iOS applications, and the second vulnerability allowed the execution of shellcode in kernel mode. So it uses these two vulnerabilities to gain complete control. Now, what is interesting about this is that the PDF format was introduced as a replacement for PostScript. PostScript was a programming language, and the PDF was different because it is descriptive. It is a vectorial format, but it is descriptive. It doesn't have instructions. But what is ironical about this is that PDFs can contain fonts which aren't descriptive, but are programs written in PostScript. Here we have a T1 font, which contains bytecode. Okay, let's take a glimpse at the exploit. You cannot see it, but what we have here is the bytecode of the exploit, and we have a warning because what happens is it pushes to the stack an impossible number of arguments for a specific function. The number is incredibly high, and this is the purpose of this is because what happens is this value is not verified, it is not checked, and it is used to perform pointer arithmetic. So what happens is that the stack pointer for this kind of bytecode is moved to a region of memory which should not be accessed, and the program later on modifies this region of memory. If you are interested in a complete analysis, you can visit the URL below. Well, how many users know that opening a PDF while having JavaScript completely disabled might involve executing PostScript instructions? And also, what is interesting to consider is the security and the necessity of T1 fonts. From a security point of view, this is from the official Adobe specification. Because Type 1 fonts were originally produced and were carefully checked only within Adobe systems, Type 1 build share was designed with the expectation that only error-free Type 1 font programs would be presented to it. Consequently, Type 1 build share does not protect itself against data inconsistencies and other problems. So in the specification, they just say, well, they should be correct. If they aren't, well, it's your business, basically. And the necessity. This is very interesting. Any of you can just guess the reason why T1 fonts are programs and not use a descriptive format like PDF itself? I couldn't come up with a reason just like you, because it's very, very crazy. I mean, it's just because of copyright. Programs can be copyrightable. Fonts, if they are like a bitmap, like an image in a sense. It says so. It's not my personal opinion. It says so in the official Adobe specification. Since Type 1 fonts are expressed as computer programs, they are copyrightable as in any other computer software. For some time, the copyright status of some types of typeface software was unclear, since typeface designs are not copyrightable in the United States. Because Type 1 fonts are computer programs rather than mere data depicting a typeface, they are clearly copyrightable. So this is just the reason. Now, ironically, DQ, the new hot thing for malware analysts and this kind of guys, is using a very similar infection vector, still a font. In this case, it's TrueType. TrueType is a font type which uses bytecode. Now, we have to consider also the differences between tablets and smartphones. They differ greatly from personal computers because they have hardware resources which not every personal computer may have, like GPS, microphone, video camera, etc. They are always carried around, and often they have a default environment like iOS, and they are used for telephone and SMS traffic. If we put ourselves in the mindset of a rootkit developer, the default environment guarantees that no third-party security solution will be there to block us, like an antivirus or a firewall. So it will also guarantee us that we'll have compatibility. If I make my rootkit work on a certain iOS version, it will work on every iOS version of the same number. GPS, microphone, video camera, and telephone are great ways to spy a person. And of course, portability means that the target will always carry the device with him and at close distance. Common security precautions on embedded devices is that applications are sandboxed and that digital signature is enforced for applications. These are very good security measures, but it also means that the use of non-executable files for infection and other malicious intents is very, very appealable. Because they escape control. Now, I want to thank you for your attention, and I want to thank also some sources which provided me with malware for my tests. My friend Giuseppe Bonfa, contagio.blogspot.com, and Offensive Computing. And if you want to follow updates on our research about the topic, you can visit our company blog. Thank you.